So let's have a look at example 4. It was a bit of an extension, but the ideas here are really important because it provides us some good information. So it says here, determine a function that has a maximum at x equals -2 and a point of inflection at x equals 1. So just to show you quickly, and keep in mind that I haven't said stationary point of inflection, I've just said point of inflection. It has a maximum at -2, so there's -2, and I don't know what the y value is there, I'm just making that up. It could be a negative y value for all I know, but that's a maximum. So it looks something like this, and it has a point of inflection, so that's probably not well drawn. Maybe something like this. There's my point of inflection. So that means that it's, remember that point of inflection is it's curving down, and then at the point of inflection you stop curving down, you start curving back up. So we get that. Now this indicates to me I've done the minimum amount of information and I've got to a cubic. So this indicates to me that it needs to be at least a cubic. It can't be a quadratic. I can't have a point of inflection and a maximum in a quadratic. I could have a quartic though. There could be another maximum over here, and I could have a quintic or blah, blah, blah. I'm probably just going to stick with a cubic. That makes my life a bit easier, okay? So I'm going to use calculus here to help develop a generalised solution on this situation. So the things I know is that at this maximum, dy dx equals 0. And at this point of inflection, d squared y dx squared equals 0. They're the two things I know for sure. So that's going to help me to build a solution to this question. As it turns out, there's a lot of solutions. And you can see that already because I could have a cubic, I could have a quartic, quintic, etc. So there's a lot of solutions, which indicates to me that I'm not just going to be able to go through and solve by substituting in and get my straight up solution. It's not going to work like that. So it indicates to me that we've got a situation where I will have too many constants, unknown constants, to be able to solve it straight up. I'll probably have to pick some values and then I'll get a solution. So let's have a look. I could have a cubic in this form, y equals ax cubed plus bx squared plus cx plus d. Is this what we did on Monday? So we did that. And what this means is that dy dx equals 3ax squared plus 2bx plus c, and it also means that d squared y dx squared is equal to 6ax plus 2b. So there's some information that I have, okay? Now you know that a point of inflection has a second derivative of 0. So the first thing I know is that at x equals 1, d squared y dx squared equals 0. And that gives me, and I'm definitely going to need to create some space here, aren't I? Oh, that was a mistake. Okay, let me just do this very quickly. So it tells me that 6a times 1 plus 2b is equal to 0. And that tells me that 6a plus 2b equals 0. I divide by 2, I take away the 3a that's left over, and I've got b equals -3a. Okay, if you've got a situation where there's multiple solutions possible, well, the best way to go about this is to find b as a value of a, or a as a value of b, or something like that. It's called a parametric solution. So it's saying later on, what I'm going to eventually do is I'm just going to pick a value of a. And then that will tell me my consequential value of b, and so on and so forth. So there's my first one. My second piece of information is that x equals 2, d squared y dx squared is less than 0. Can anybody tell me why that is? Not you. Anybody else? Yep. It's so the rate of change is heading down. Why is that? How do we know that from the question? So it's going down. What's that shape? It's a maximum. The question says it's a maximum. So if we go back to our initial rules, it was stated that a maximum has a second derivative that's less than 0 because the gradient is going from a high positive to a high negative, so it's doing that shape. Okay? So if the gradient is decreasing, then the second derivative is less than 0. It's negative. I've just written less than 0. So at x equals 2, the second derivative, which is 6a times 2 plus 2b is less than 0. And that means that 12a plus 2b is less than 0. Now I know my value of b is negative 3a, so it means that 12a plus negative 6b is less than 0. Oh no, not negative 6b, negative 6a. And that tells me that 6a is less than 0, which tells me that a is less than 0. Except I've got it wrong, haven't I? No, wait, it's negative 2. My apologies, I've just realised. I remember in my mind, I'm like, no, that's not what it was. Because the maximum was at negative 2. Sorry about that. So the maximum's not at 2, it's negative 2, we're going to get there. So we get 6 times that, I get a negative here. That gives me a negative there, that gives me negative 18a, and that gives me a is greater than 0. When I divide by a negative, I flip the inequality. Is that all right? Cool. Okay, so I got that slightly wrong at the start with my substitution of 2, but we get a is greater than 0. So a is greater than 0, b equals negative 3a. The third thing I know is that at x equals negative 2, dy dx equals 0. Because it's a maximum, it's a stationary point. So I know it's a stationary point. So I put that into my dy dx, which I can't remember, that's this one here. And I get 3a times x squared, which is negative 2 squared, plus 2b times negative 2, plus c has to be equal to 0. The first derivative is equal to 0. And that gives me, negative 2 squared is 4, so it gives me 12a minus 4b plus c equals 0. And b is equal to negative 3a, we determined that earlier. So I get 12a minus 4 times negative 3 plus c equals 0. Oh, sorry, negative 3a. That gives me 12a plus 12a plus c equals 0. 12a plus 12a is 24a. I subtract it and I get c equals negative 24a. Okay? Now, if I go back to my original function, I had 4 unknowns. And that was, I also have d. But I've run out of piece of information. I know I've used the fact that negative 2 is a maximum, and I've used the fact that because it's a maximum, the second derivative is less than 0. And I've used the point of inflection information to its full extent. There's nothing more I can do. So I can't find a relationship between d and all the other things. But actually, when I think about it, that makes sense. Because if you go back to Unit 1, and this is a bit of a revision on Unit 1, if we add d to a function, all that does to the function is transfers it up and down, or translates it up and down. So if I pick up this function and translate it up and down, if I actually think about it, it doesn't really matter what d is. I'll still have a maximum here, and I'll still have a point of inflection there. It'll just be a bit higher or a bit lower. So it doesn't matter what d is. I don't know what d is, but I don't really care. D could be anything, and I'll still get the same outcome. So I'm going to let d be anything. And I've also got this. I know what b is. Oh, that wasn't meant to happen. I know what b is in terms of, still not swapping, there we go. I know what b is in terms of a. I know what c is in terms of a. I know that a has to be some number greater than 0. Who would like to pick a number for me? 2 sounds good. So if a equals 2, then b equals negative 6 because b is equal to negative 3a. C is equal to negative 24a, and negative 24 times 2, so negative 48. And d is equal to, we've already determined we don't care, it's something, so let's make d equal 7. And our function is y equals 2x cubed minus 6x squared minus 48x plus 7, and that will give us a maximum at negative 2 and a point of inflection at 1. And it's just one example. Dylan gave me another one that was different. And the interesting thing was I sat and I talked about this with, it's on the board still. There we go, I haven't even rubbed it off. Talked about it with Connor, and we built that concept and that understanding as a generalised solution Dylan came over completely independently with his solution, which turned out to be the solution you get if you substitute in a equals 1. So you can get it both ways. And because we're interested, let's really quickly throw that, stop doing that, on Desmos. So I had, and just let's have a quick look at what it looks like. Spins y equals 2x cubed minus 6x squared minus 48x plus 7. My zoom is not very good because we chose 2, it's quite large. So let's change that to, I don't know, negative 100. See if that was way too big. Oh wait, no, I want that to be the same. I want that to be from negative 3 to 4 or something like that. And then I want this to be negative 100. See if that works. No, that doesn't work. Does it? Oh no, it might work. Let's do 200, flatten it out a bit. And we go quite high here to get the 2 in. So we'll go up to 200. Yeah, there we go. Okay, so 2, we can see 2 is a maximum. It goes up to 63. And at 1, and you can't really see it on here, but that point 1, hopefully you can kind of see that if I move along this graph, I'm curling my hand down, still curling my hand down as the gradient changes, and then at this point, I'll start to curl my hand back up. That's what a point of inflection does. And the second derivative is 0 there because the gradient is not changing for that moment. Decreasing, 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 0, and then increasing, increasing, increasing. Okay? Unit 3 has another differentiation topic, and we'll go and talk a lot about increasing and decreasing functions. So that'll come up pretty significantly. But for now, as long as you can do a few of these ones, you can get an understanding of what's happening. It's all about the curl of the hand. Really, that pretty much explains what's happening with the function. Cool. I'm going to stop that there.